So, we want to arrange the counting numbers, put them in order. Alright, done. But that one's a bit boring, isn't it? Let me make a new ordering by making 4 larger than 5. This is no longer the usual ordering that we're used to, but it's a valid ordering nonetheless. But while it's technically a new ordering, it's not very interesting, is it? It's still basically the same. What is a bit more interesting is if I instead declare 5 to be larger than every other counting number. Now this new ordering holds a key property that the usual ordering of the counting numbers doesn't have. It has a largest element. To really get to the bottom of the difference between these two orderings, we want to talk about maps from one set to another. We can visualize a map from one set to another by drawing arrows from the first set to the second. In this case, the element 3 of the first set gets mapped to the 7 in the second set, and the element 4 gets mapped to the element 5. It's called a bijection if every element in both sets have exactly one arrow, and we're going to call a bijection order preserving if, when both sets are written in their corresponding ordering, the arrows don't cross one another. An order preserving bijection doesn't change the order. We then define that two orderings have the same order type if there exists an order preserving bijection between the two. Back to our original examples. The set where 4 is larger than 5 has an order preserving bijection to the usual ordering. We can just draw the arrow straight down. This means these two orderings have the same order type, which we call omega. The set where 5 is larger than every other number, however, does not have an order preserving bijection to omega. There is no way to map the element 5 to an element of omega without crossing some other number. This ordering therefore has a different order type from omega, which we call omega plus 1, because it contains a copy of omega and has another element on top of that. Now, I think this is pretty neat. It's the same set, but we have an ordering that is straight up larger than the usual ordering of that set. But of course, we can make even larger orderings by moving even more elements up front. We can make omega plus 2, omega plus 3, even omega plus 1,000,000 if we wanted to. But how far can we take this? Can we go as far as to make omega plus omega? Now we can't just haphazardly move an infinite number of elements. We need to still be able to account for where every element is in the ordering. Otherwise, it's not an ordering. So we need a strategy. We need to be systematic. And you might have already guessed how we're going to do this. There are many ways which this can be achieved, but the simplest way is to have all the odd numbers be greater than every even number. The even numbers will form an ordering of type omega, and then after every single even number, we have another copy of omega in the form of the odd numbers. This gives us an ordering of type omega plus omega, also known as omega times 2. From here, we can make even larger order types by moving singular elements up front again, creating omega times 2 plus 1, omega plus 2, and so on. But more interestingly, we can use a similar scheme to create omega times 3, by first writing down numbers divisible by 3, and then the numbers with a remainder of 1 when you divide by 3, and finally the numbers with a remainder 2 when dividing by 3. And certainly, we can make omega times 4 by dividing the numbers into 4 sections, and putting the sections one after another. And we can make omega times 5, and omega times 6, omega times 1,000,000. So the obvious question now is, can we make omega times omega? Well, not with the strategy we're using now. So let me offer an alternative way of constructing omega times n. We start by constructing omega times 2 similarly to how we did before, but we put the even numbers to be larger than the odd numbers. From here, we'll take the even numbers and split them up into 2 parts. One where the numbers are divisible by 4 and one where they aren't. We can now move the numbers divisible by 4 to the end, creating omega times 3. So here we have divided the natural numbers into 3 parts: the odd numbers, numbers that can be written as an odd number times 2, and numbers that have more than one factor 2 in them. From here we can keep going, removing all the numbers that are divisible by 8 from the last group, and putting them at the end, creating omega times 4. And this is a process that, unlike the previous one, can be taken to infinity. We get a scheme where a counting number written in the form of 2 to the n times the kth odd number will be in the kth position of the nth omega. Thus, we have managed to create an ordering of order type omega times omega, also known as omega squared. I want to take a minute to just appreciate how far we've come. Because remember, we're still dealing with the counting numbers. And it's not some esoteric or bigger set. Right? It's just good old 5 and 17 and whatever. Yet we've managed to order them in an order type that is literally the square of our usual ordering. I think that's pretty neat. But of course we're gonna keep going. Now we can make omega squared plus 1 by simply moving an element to the end. We can make omega squared times 2 by moving every other element to the end, but let's jump right into the good stuff. How do you make omega to the third power? Well, one thing we can notice is that just like you can write every number as some power of 2 times an odd number, we can also write every number as some power of 2 times some power of 3 times some number divisible by neither 2 nor 3. If this isn't immediately clear, consider writing any given number in its prime factorization, and then just extracting the 2's part and the 3's part. So any number can be written as 2 to the n times 3 to the m times r of k, where r of k gives the kth number that is not divisible by either 2 nor 3. Well, first we can get omega squared by simply doing as before, 2 to the n times r of k. But to have ordered every counting number, I have to have one copy of this omega squared times 3 to the 0, and then one copy of it times 3 to the 1, and then one copy times 3 to the second power, and so on. So this does indeed give us omega copies of omega squared, that is to say, omega cubed. To get to omega to the fourth power, we need to be a bit careful. One might accidentally assume that we write it as 2 to the n times 3 to the m times 4 to the l times some number. But that would be a mistake, since we've already covered the powers of 4 within the powers of 2. So the next number that we want to pull out of r of k is 5. So taking the counting numbers and ordering first by r of k, then by powers of 2, then by powers of 3, and finally by powers of 5, give us omega to the fourth. And as usual, we can keep going, where we take note that the powers that we extract from r of k are exactly prime numbers. I extract 7 and we get omega to the fifth power, and when we extract 11 we get omega to the sixth power, and so on. And this process we can continue indefinitely, and all the way up to infinity. This gives us finally that if we order the counting numbers lexicographically by their prime factorization, we get an ordering of type omega to the omega. That's a big ordering! Now, we're approaching the end of this video, but I want to leave with one final trick for obtaining even larger order types. And we somewhat explored this strategy before when we constructed omega times 3 by applying the scheme we got to omega times 2 to just the latter half of omega times 2. I'm going to call this technique nesting. You might also call it recursion. So if you look at our omega to the omega ordering, you will notice that each prime number is raised to the power of some counting number. These exponents can then in their own right be ordered in increasingly convoluted ways. As an example, take just the 2's exponent. We can choose to order this exponent in the same way that we just ordered the counting numbers as a whole. We then have that the 2's exponent is a copy of omega to the omega, and the rest of our prime factorization is another copy of omega to the omega. Therefore, we have an ordering that is in total omega to the omega times omega to the omega, which can be simplified to omega to the omega times 2. Now, I encourage you to play around with these nestings and see what exciting order types you can arrive at. Omega to the omega square, omega to the omega to the omega, maybe even the elusive epsilon naught, a power tower of omegas. Playing around with these is great fun, and I wish you good luck, and thank you for watching.